Only about NASCAR, about ethanol as a racing fuel, but we'll also talk about it just as a general automotive fuel. I'm not here to give you a commercial for ethanol. I'm here to tell you about the pros and the cons and let you make up your mind for yourself. But I think in the end you'll find that as we discuss all the issues surrounding ethanol, you'll come to the same conclusion that I have, that it's an excellent automotive fuel and something that I hope plays a greater part in our future moving forward. So let's start with a little overview of what ECR Engine is for those of you who are not familiar with it. It is a high-performance engine development and manufacturing company located up in Welcome, North Carolina, about an hour from here. We have 130 enthusiasts there that produce over 600 engines a year for racing, primarily for NASCAR, where we participate in the Cup Series, Xfinity, and the Truck Series, as well as we provide the engines for the Cadillacs in the prototype division of the Premier Road Racing Series in North America. Been doing this for a long time. Those of you who have been around for a while, which isn't very many of you, our claim to fame up in RCR was back in Dale Earnhardt's days and bringing him through his years of success in NASCAR. And since then, we've had the pleasure and honor of working with many other drivers since then. So most of what we're going to talk about today, engine-wise, is information that comes from a Cup engine. A NASCAR Cup engine has its roots many, many years ago, back actually to the small block engines of the 1960s. These are V8 engines that are 350 to 358 cubic inches, which is 5.8 liters. I put the word stock in parentheses because presumably by rules, the engine is a stock cast iron block and aluminum cylinder heads. But we have done this exercise a number of times over the years where we look over the parts list for our engines, which consists now of over 4,000 parts if you can count all bolts and washers, hoping to see if we had one part that actually would qualify as stock, and so far we haven't been able to find one. So there are no parts on these engines that are actually parts that are on automotive engines that you would buy at a dealer. But nevertheless, the architecture as far as the displacement and the bore spacing and things like that are representative. Compression ratio is limited in the rules. It's a fairly archaic architecture. I don't know, how many of you are engine people in the room or kind of know engines? Okay, well, this is good. Okay, so I'm not speaking in a foreign language up here on a lot of this. A push rod 2-valve per cylinder valve train, that's a pretty old archaic architecture. So what you have in NASCAR is you have this interesting mix of a really old architecture, but with state-of-the-art as far as materials, coatings, surface finishes, processes. And when you combine those two, that's how we're able to take an engine, an actually aspirated engine that's only 5.8 liters, and when we don't have any of the airflow restricting devices that NASCAR likes to put on them, these engines currently put out about 850 horsepower. That's at around 9,000 RPM, and about 530 foot-pounds of torque. Restricted engines for super speedways, that's one of the more restricted venues that NASCAR puts on us. They put an air restricting device where the air has to pass through 4 holes that are basically about the size of your little finger, and that reduces the power down to only around 420 horsepower. That's for super speedways like Daytona and Talladega, where even at that power level, average speed over a lap will still exceed 200 miles an hour. If we were to go there with the unrestricted engines, average speeds would exceed 240 miles an hour, and at some point it just gets a little ridiculous and a little dangerous. So try to keep the speeds closer to 200 miles an hour. So what in the world is the difference between a race engine and a production engine? I said architecturally they're similar, but the development philosophy that you use to create them is much different. In the production engine world, there are a number of criteria that you have to work around, all of which are weighted similarly. Obviously, the engine has to last, in the course of a production engine, has to last 150,000, 200,000 miles. It has to make the power you want. Fuel economy is always a concern. Drivability, noise. You have to worry about emission standards. It has to fit in the car. You have to be able to afford it. You have to be able to make it. So a production LT1 engine, which mimics what our engines are as far as bore sizes and displacement, makes around 460 horsepower and 465 foot-pounds. In racing, we have a different set of requirements. Number one is reliability and durability. because of course you have to finish if you want to win. But our reliability or durability is race distance plus 1 mile. So in the case of a 500-mile race at Charlotte, our goal would be to produce something that lasts for 501 miles. If it lasts for 510 miles, you've probably over-designed some of the components and are giving up some power in doing that. If it lasts for 490, you had a very bad miscalculation, and need to work a little harder the next time. Power curve, of course, is ultimate importance. Fuel economy, don't worry about it so much. We'll figure out a way to make it fit. They cost a fortune. They take forever to make. So the criteria gets less and less stringent with race engines once you get past that it has to last for race distance plus 1 mile, and it has to make a lot of power. So in order to do that, these engines are stressed pretty heavily. They're highly stressed to produce the output they do, and to produce that output, it's highly dependent on favorable fuel and lubricant properties. Now let me show you a little video here. This is one thing that I wasn't sure how to do remotely, so we'll try it this way. Well, that didn't work either. Let's try it this way.
We're at 333 degrees cooling out, 116 psi in the block, and 105 in the tank.
Whoa! Okay, so that one didn't make it to race distance plus 1 mile. But that illustrates for you the amount of force that's in these engines, what's going on when they run. And when they don't make it, the results can be pretty spectacular and depressing if it's your engine. Now, for fuel history of NASCAR, for many years NASCAR spec fuel was a leaded aviation fuel, 112 octane. This went all the way up to 2008, long after leaded fuel was gone from the automotive world. The reason that we retained it in NASCAR was we just needed the octane, and lead was an excellent source of octane. But it was always a little scary because we're intimately in contact with the fuel all the time. We're breathing it, we're getting it all over our skin, we're wearing it, we're swimming in it. And knowing that we were working with something which is a known blood toxin poison wasn't that comforting. So it was nice in 2008 when NASCAR finally adopted an unleaded fuel. However, in order to get to the octane that we required, we had to use over 40% aromatic concentration in the fuel. And aromatics are benzenes, toluenes. Most of the aromatic constituents are known carcinogens. So what we did was we just changed the way we were going to die from lead poisoning to cancer. So still not comforting, but we did with it what we could. And then in 2011, NASCAR changed to an E15 fuel. The nice thing about that is ethanol inherently has a very high octane, something we'll talk about later. And what that allowed us to do is displace over half of the aromatics in the fuel with ethanol, ethanol being a much safer additive, and that's what we've been racing ever since. E15 is 15% ethanol. If we could increase the ethanol concentration to 30%, then we would be able to eliminate the aromatics altogether, which is certainly something that I hope happens here in the not too distant future. So what really is an engine? An engine is simply an energy conversion device. You're taking fuel, the chemical energy in fuel, and you're passing it through this energy conversion device that's translating that to mechanical energy at the wheels which propel your vehicle. In the case of a NASCAR engine, we put about 2,430 horsepower into the engine in the form of chemical energy. We pass it through this energy conversion device where we have a thermal efficiency, a volumetric efficiency, mechanical efficiency associated, and we get about 850 horsepower out of the other end. Now this horse here is looking concerned and a little confused because he expected a lot more than 850 of his friends when he considered that he put 2,430 in. But that's actually pretty good efficiency for an internal combustion spark ignition engine. That's what we're dealing with. And that's depressing on the surface to know that we're that inefficient in transferring this chemical energy to mechanical energy. But on the bright side, that says that there's plenty of room for innovation, that hopefully someday many of you in this room will contribute to making it where to get this amount of power out, you get to put less in, or if you put this much in, you get significantly more power out. So now let's concentrate more on that fuel, because obviously that's the input to this whole process, what drives these things. I know many of you have, many of you know engines. I'm sure chemistry, I'm sure a lot of this is rudimentary to many of you. But in order for combustion to happen, we have to have fuel and air. And if they're mixed in the perfect proportions, then they'll generate as outputs carbon dioxide and water. If they're not in the absolute correct proportions, if you have too much fuel, that would be considered a rich fuel and air mixture, where then the products of the combustion will be CO2 and water plus excess fuel. If you have excess air, which we've done down here, then the products of the reaction will have air included in well. There'll probably be some CO, some CO would be up here, I'm sorry. There'll be just excess air that happens here. So the object is, for best emissions, to have perfect amount of fuel and air. Let's look at the difference now between ethanol and gasoline. Ethanol shown on the top, just 2 carbon atoms, has a hydroxy radical attached. This would be a stoichiometric reaction here. These ratios that we're talking about here are very important. And as you look at them, I'm giving the thumbs up here because every ratio here is favorable from a combustion or environmental perspective relative to gasoline. So here's ethanol hydrogen-carbon ratio. There's 3 times more hydrogen atoms than there are carbon atoms. There's the oxygen-carbon ratio is a half. The research octane number of ethanol is around 109. The heat of vaporization of ethanol is around 110 kilojoules per kilogram air. We'll go over each of these individually here in a minute. Comparing to gasoline, the hydrogen-carbon ratio is around 1.8. There is no oxygen attached to the gasoline. The octane number is around 93. Heat of vaporization is about 40. So now I want to go through each of those parameters individually and go over what the differences between ethanol and gasoline are and how those generally work in your favor. The first is the hydrogen to carbon and the oxygen to carbon ratio. First of all, the more hydrogen you have relative to carbon, hydrogen burns very cleanly. Obviously the products of combustion of hydrogen and oxygen are water. That's a pretty darn clean reaction. Also then, having some oxygen bound to the fuel, so this is now we're getting to the oxygen to carbon ratio, having some oxygen bound to the fuel increases the oxidation efficiency. So when you blend gasoline with ethanol, that reduces the carbon monoxide and the unburned hydrocarbon emissions because you have that oxygen atom that's there part of the fuel. Let's burn a couple of things here and you'll get a very vivid description of what I'm talking about. So what I have here, we'll start with, this is just some Sunoco gasoline. This is actually like premium gasoline without any ethanol in it. I'll pour a little bit of it on here, hopefully not spill it on the floor. Did spill some on the table. The object is not to burn your building down. I thought it was funny when I put the picture of the Hindenburg up there, but afterwards I thought maybe that's not very funny, but anyway. Okay, so there's how gasoline burns. Obviously, I don't know if you can see, everybody can see it, you can see the carbon coming up. If I put this thing right over here just for even a little bit of time and hold it up, you can see the carbon emissions coming off of the combustion. What this is you have carbon that's not finding oxygen and it's being emitted in the form of soot. There is no oxygen in the fuel, so this is purely a diffusion flame where the fuel has to evaporate and come up and meet with air that's coming down from the environment here. Let's put this one out. That worked pretty well. Okay, let's look at ethanol now. I happen to have some ethanol. I have some right here. I know you guys recognize this, admit it. Another advantage of ethanol. Takes me back. I was young once, just so you know. Let's see, let's put this one up here. Uh-oh. Once again, the object is not to burn down your classroom here, although I know on bad days some of you might prefer that. Let's move it way over here. Okay, let's start this one out. Okay. It's burning. Ow, I guarantee you it's burning. You want to come and, can you see it? Can you see it burning? Can everybody see it burning? Oh, yeah. Can you see it burning? Okay. Well, then you all go to sleep. Okay, so what I'm going to do now, it is burning, I promise you. And if you had some marshmallows and graham crackers, we can make s'mores over this. I'll hold the paddle here for a minute, and we can just kind of look and see what happens. You know, we can look at the paddle, and the paddle's a little warm, but it's perfectly clean. So the issue that we had with gasoline, where we produced carbon that could not find oxygen and thus resulted in soot emissions, here because we have oxygen that's contained in the fuel providing somewhat of a pre-mixture, we have a much, much cleaner combustion situation. So that kind of vividly shows what the combustion characteristics are different between ethanol and gasoline. Let me go ahead and put this one out. Make sure it's really out. It really was burning, I promise. Okay. So let's move on to the next property. I'm going to spend a little bit of time talking about this one. This is the octane difference between ethanol and gasoline. As we mentioned, remember before in the slide where we compared the chemistry of the two. I wish this was lower. I feel like I'm going to have a sore neck by the time I'm done. But remember when we compared the chemistry, the research octane number of ethanol was around 109 and gasoline was around 93 or so. Octane quantifies the susceptibility of a fuel to auto-ignite. Higher octane values imply lower susceptibility. So what does auto-ignite mean? That means you start the fuel. In this case, we had a spark in this engine over here. It's kind of a two-dimensional representation. The fuel propagated across the chamber, or the flame propagated across the chamber. Before it got to the end, it got hot enough that fuel and air ahead of the flame started to auto-ignite on its own. So therefore, you had several ignition sources. What that causes is the pressure to increase then rapidly because you're burning in multiple locations. Knock refers to the sound that results from spontaneous ignition of the air-fuel mixture ahead of the normal propagating flame and the subsequent cylinder pressure oscillations that occur. Knock typically occurs near the end of the combustion event and is characterized by rapid fluctuations in cylinder pressure and a distinctive pinging sound. Now, you don't hear that too much on modern cars anymore because they have accelerometers mounted on the side of the engine where once they start to knock, it starts retarding the spark and makes calibration changes so that you don't hear it anymore, but you're degrading the efficiency in order to keep it from doing that. Power can actually increase with knock because the end of the air-fuel mixture burns nearer to TDC. Here's some cylinder pressure. I'm going to get the right button one of these days. Here's some cylinder pressure versus crank angle plots here, where the black one, which has 11,000 kPa peak pressure here, has no knock. The red curve has a little bit of knock. It's about 13,000 now is the peak pressure here. The green curve has very heavy knock. You can see it ringing, and you see the initial knock pressure peak here is almost doubles the peak pressure of what the engine was generating without the knock. Too much of that and you will be walking very soon because that's generating pressures and temperatures which are not what the engine was designed to handle. A couple more things on knock because this is a key part of ethanol and what it can do for the automotive industry moving forward. Knock initiates far away from the spark plug when combustion is near completion. So here's the spark plug over here. I drew some little concentric circles that kind of show how far you are area-wise across the chamber. Knock's going to occur at the very corners late in the combustion event. Could potentially initiate along some sharp edges of the pocket or near the perimeter of the combustion chamber on the hotter exhaust side, right around in these areas. Knock is measured by just a cylinder pressure sensor looking at rates of pressure rise. So when knock happens, like we said, the pressure rises very, very quickly. So this is looking at rate of pressure rise versus engine speed in a sweep. So we're going from 6,500 RPM up to 10,000 RPM here. All 8 cylinders of the engine are plotted. You see that the red here, which is cylinder 2, rates of pressure rise go from 500 to several thousand, indicating that we have extreme knock going on in that case. When you take apart an engine that's knocked or that's failed and you wonder if knock had anything to do with it, normally the telltale signs are you'll see on the edge of the piston, far away from the spark plug, you'll see actually some material pitted out on the edges. Now, when does knock occur? Well, knock occurs when the integral of temperature times time of the air-fuel mixture is high. So that's why it's the part farthest away from the spark, because that's the last part that gets burned, so that's the time. The temperature part is if you're at a high load, if your compression ratio is high, you have things here that encourage knock. High compression ratio, low engine speed. That means you have more time from when the physical time from when the spark is discharged. Temperatures are high. Charge dilution is low. Air is dry and dense, so you don't have moisture. A lot of deposits, high amount of spark advance. Compression ratio high. This is the big one because those of you who have been through engine courses, I'm sure one of the first things you learn is engine efficiency, at least ideally, is directly proportional to compression ratio. If you want to get better fuel economy, one of the first things you need to do is increase the compression ratio of your engine. So here's a formula for ideal. At 10 to 1 compression ratio, you get about 50% efficiency from this equation. At 13 to 1, you get about 54% efficiency. You say, well, that's only 4 points. Well, you take the ratio of the two, and it's closer to 10% gain in thermal efficiency, which is a strong gain. So therefore, octane limits the efficiency potential of engines through the ability to implement a high compression ratio. Ethanol is the safest, least expensive octane booster. We said before, if you could have 109 octane fuel, you could have extremely high compression ratio in engines and knock would not be an issue. Next, I want to talk a little bit about heat of vaporization. Heat of vaporization is the amount of energy required to convert a substance from liquid to gaseous phase. If you take some of, I better cover this up before it all evaporates away. If you take some of this and pour it on the back of your hand, and then blow on the back of your hand, when it vaporizes, you'll feel your hand get very, very cool. That's the heat of vaporization at work there. And the heat of vaporization of ethanol is almost 3 times the heat of vaporization of gasoline. Fuel vaporization is beneficial in engines because it cools the incoming charge, analogous to running on a much colder day. So the more ethanol that you inject into the mixture, as it evaporates, it cools the mixture, the air and fuel mixture coming in. And once again, that's going to help you from an efficiency standpoint, and it's also going to help you from a knock or compression ratio standpoint because you're starting up with a cooler mixture. So like I said, ethanol has nearly 3 times the heat of vaporization of gasoline, providing greater cooling and enhancing the already excellent octane characteristics. Octane ratings are done at a fixed inlet charge temperature. So when fuels are rated, the rating process that the government uses a fixed temperature of the air-fuel mixture going in, so therefore you don't get to take advantage of the characteristics of ethanol in that octane rating. Power also increases with a cooler intake charge because the density increases. If you want your car to go faster and have more fun, then you want to get out on a nice, cool, dry day. So summarizing ethanol combustion, high hydrogen content and entrained oxygen reduce unburned hydrocarbon and partially oxidized carbon emissions relative to gasoline. Once again, that's the hydrogen and the oxygen. High octane reduces propensity to knock and aligns with automotive industry trends towards smaller displacement, high specific power engines. You see V8s going away, being replaced by V6s that are twin turbocharged or boosted in some way. In order to be able to accommodate those high specific power, that's where you need the octane. High heat of vaporization further increases octane above published values and provides a power boost via charge cooling. So those are all nice benefits, good advantages. You will often hear disadvantages of ethanol as well. So let's go ahead and review those and see what's real and what's imaginary. What we're going to talk about are the heating value of ethanol relative to gasoline, corporate average fuel economy standards and what it requires to meet those, the hygroscopic nature of ethanol, and finally the stoichiometry of ethanol versus gasoline and how that applies to boats and lawnmowers and weed whackers and things like that. So let's start talking first with heating value. Lower heating value of gasoline is about 116,000 BTUs per gallon. I know nobody uses BTUs anymore, but NASCAR still uses BTUs. So lower heating value of ethanol is about 76,000 BTUs per gallon. It's 34% less energy in a gallon of ethanol than there is in gasoline. So all else being equal, pure ethanol would produce 34% less fuel economy than pure gasoline because of the heating value reduction. That is if you were running on pure ethanol versus pure gasoline. Sometimes you'll hear people say, oh, well, I don't want ethanol in my fuel because ethanol is 30% worse fuel mileage. Well, if it was pure ethanol, that would be true. However, I'm just saying, E10 is what's commonly available in the pumps, so that's 10% ethanol. So now instead of 34%, you're talking about 3.4%. At E15, you're talking about a 5.1% energy reduction using an E15 gasoline blend as opposed to pure gasoline. So typical E10 gasoline does have about 3.4% less energy content than ethanol-free gasoline. However, E10 gasoline costs 20 to 40% less than ethanol-free gasoline. E15 gasoline costs yet another 3 to 5% less than E10 gasoline. So if I'm going in there and I have the opportunity to buy E10 or E15, which is a number of stations in North Carolina do, if I can save 3 to 5% in costs for a 1.7% delta in energy, once again, what I'm listening to is my wallet, and my wallet says that's the right thing to do. Ethanol blended gasoline is a bargain on a miles per dollar basis. So although you can make an argument that, okay, I'm going to have this ethanol gasoline blend, I'm going to get a little bit less gas mileage, but really, to me, what I care about as a consumer is how much does it cost to drive my car? What's the long-term operating cost of putting fuel in it and driving it? And that's where ethanol blended gasoline will provide considerable savings over not having the ethanol there. Next one is CAFE, corporate average fuel economy. Current regulations require a fleet average of 37.5 miles per gallon for each manufacturer in 2017, increases to 54.5 miles a gallon in 2025. President Trump has postponed the 2025 requirement pending further study because some reality set in there that that's going to be virtually impossible to do. Regulating the automotive efficiency by volumetric consumption is a really bad idea. It works against the ethanol industry, but it's just not a good idea, and I'll explain why here. Ethanol is a renewable resource. It's domestically sourced. It's inexpensive. We just talked about relative to gasoline. It's secure. It's clean. It's efficient. It gives us a way to be in control of our own energy destiny as a country. The one thing ethanol is not is consistent with reduced volumetric consumption. So like we talked about, you can use ethanol to increase your octane, allow you to get higher compression ratios, allow you to get higher efficiency measured as energy out versus energy in. But from a volumetric standpoint, that's the one place where ethanol is not loses some of its favorability. Here's another graph trying to get that point across. Engine efficiency increases with increasing compression ratio. Efficiency gains are much greater when compression ratio increases or coupled with downsizing. So this is compression ratio plotted. This is efficiency plotted as a function of compression ratio. This is the efficiency gain. If you just change the compression ratio, you can get some amount of gain. If at the same time you downsize the engine, because increasing the compression ratio is going to allow you to get more output of the engine, then your efficiency gains can be much worse. Now, if your mechanism allowing you to do this is increasing the concentration of ethanol in the fuel, then you're writing down this curve here, where as you increase the percentage of ethanol in the ethanol gasoline blend, your relative energy content is going down. So fuel energy content is decreasing as you're increasing that ethanol. So you got an energy content reduction in percent, but you've got an efficiency increase in percent. And depending on how those balance out, you're always, in all cases, you're going to be more efficient from a thermal efficiency standpoint, but from a volumetric fuel standpoint, you might not be. Fuel economy in miles per gallon improves only if efficiency gains are greater than energy content losses. Ethanol is a great fuel, but our current CAFE philosophy does not reflect many or virtually all of the benefits. Other efficiency metrics, such as CO2 emissions, make much more sense if the objective is to have the government encourage consumers and in the automotive industry to produce more efficient engines. There are certainly plenty of examples around the world, and I think most countries around the world regulate engine efficiency off of CO2 emissions and not off of a fuel economy miles per gallon number. Switching to a system like this would make ethanol very, very much more favorable for manufacturers than our current laws do. Let's watch a couple more videos here. This has to do with hygroscopic. Water is not soluble in gasoline. Small amounts of water also are soluble in ethanol gasoline blends. Is this a problem? Some people would like you to believe it is. In my opinion, water solubility is an advantage. Let me show you a couple of videos, easy little experiments here. This is a beaker that has a little over 1,200 cc's E15 fuel directly out of our fuel tank. Should be dry. We're going to go ahead and add 9 cc's of water to it. The 9 cc's of water represents 0.75% water concentration. You can see as we add the water, it goes right to the bottom of the beaker. It doesn't immediately mix in with the fuel. But if you look real closely, you'll see where the water is starting to soak in with the fuel at the bottom. Now what we're going to do is we're going to take this beaker off of here. I'm going to leave you for a minute. I'll come back when we're ready to stir the water in. Here we are with the water in the beaker, 0.75%. We're going to go ahead and stir it up now. It's not that easy to get it into solution. You've got to stir pretty good. But you can see as it keeps on stirring, the fuel starts to look like it's getting a little bit opaque, but then it clears up again, and voila, all the water has gone into solution. That's 0.75% water. Okay, so that's what happens when you do that experiment on a E15 mixture. Let's do that same experiment now with gasoline. This is a beaker filled with 1,200 cc's of Sunoco 260 GTX, which is a premium gasoline, a hydrocarbon gasoline without any alcohol content. We're going to add 9 cc's of water now and see what happens. You can see as the water is added, just as it did with the E15, the water goes directly to the bottom of the beaker because it's heavier than the gasoline. Now let's go ahead and stir it, see if we can get it to go into solution. Now if you recall, when we did this with the E15, the gasoline immediately started to go into solution as the fuel became translucent, and then when it was totally into solution, the fuel, once again, there was no phase separation between the water and the fuel. We'll go ahead and stop stirring now. You can see here, as soon as he stops stirring, the water is still out of solution and at the bottom of the beaker. So no matter how long he stirs, the water is not going to dissolve into the gasoline. Thus, you're going to have phase separation immediately as soon as you get any water into the fuel. So that's definitely a difference in characteristic between an ethanol gasoline blend and pure gasoline. I consider that actually an advantage. Some people would try to convince you that's a disadvantage. I guess you can make up your own mind, but it's a pretty easy experiment to do. It is interesting, however, that the vast majority of fuel additives for treating gasoline alcohol blends contain primarily alcohol. You won't find it on the bottle, but if you go to the website and load the MSD sheets, you'll find that the products that are sold as fuel treatment to fix alcohol gasoline blends are actually bottles consisting primarily of more alcohol. So, finally, let's talk a little bit about stoichiometry and as it applies to small engines. Recall that combustion chemistry of gasoline and ethanol differ. The stoichiometric air-fuel ratios are as follows. Gasoline at 14.7, that means it takes about 14.7 pounds of air per pound of fuel to have the perfect mix of air and fuel in gasoline. For ethanol, that reduces to around 9.0. That implies that E10 is around 14.1, E15 is around 13.8. Passenger cars and trucks and large inboard boat engines operate in closed loop, where an oxygen sensor automatically adjusts the air-fuel ratio for optimum operation. So the fact that you require for optimum operation a different amount of air relative to the amount of fuel as you change the percentage of ethanol is compensated for automatically in the control system of those engines. Many outboard engines and lawn engines, mowers, chainsaws, weed whackers, etc., do not have oxygen sensors and thus operate in an open loop mode with a fixed ratio of air to fuel. So they either have a carburetor or maybe in some cases they're fancy enough to have a fuel injector, but the calibration is fixed and it cannot compensate for changes in the percentage of ethanol. So therefore, as you increase the amount of ethanol in the fuel, then you're getting away from what would be an optimal mixture in those devices. Calibrations are typically, however, very rich in those devices, in the 10 to 12 range. Excess in fuel to provide extra cooling at the expense of efficiency in the environment They don't have emission standards for lawnmowers, so manufacturers feel empowered to go ahead and just throw tons of fuel at them and let the fuel be one of the mechanisms that helps keep the engine cool. Blending ethanol into the gasoline makes the mixture less rich. However, that phenomenon is slightly offset by the cooling effect of ethanol that we talked about. So the bottom line is E10 to E15 is not a problem in these small engines. However, if you were to put enough ethanol in the fuel to make it where you actually start to get to stoichiometric or lean stoichiometric, then there is a potential. So, I wouldn't recommend that you run E85, for instance, in your lawnmower, but running a normal E10 blend will not cause you any issues. So let's summarize our discussion of disadvantages and myths and whether or not they're really disadvantages. First statement you might hear is heating value of ethanol is less than that of gasoline, resulting in lower miles per gallon with ethanol gasoline blends. Well, that's true, but the cost of the fuel drops much faster than the fuel mileage, making ethanol gasoline blends a bargain from a miles per dollar perspective. Fuel mileage impacts at typical blend rates are very small. So I guess the statement is correct, but really I don't consider it a disadvantage. I consider it an advantage when you start talking about the economics of it. Next, the ethanol is of limited benefit to automotive manufacturers seeking higher CAFE. That also is true. However, ethanol is a gateway to higher thermal efficiency and consistent with current engine design trends towards higher compression ratio and higher specific power. Hopefully the government will soon appreciate that. Legislating efficiency indirectly via volumetric consumption is a bad idea. Next one, ethanol absorbs water and harms boat engines. Well, I disagree with that. It does absorb a little bit of water, but any water in the fuel system is an issue for boaters operating on pure gasoline. Any water, a drop of water. Ethanol provides some relief. There is a point at which you exceed the solubility limit, but it does provide some safety factor. Ethanol ruins small engines. Disagree with that too. Small engines are calibrated extremely rich so that the fuel can aid with cooling. Ethanol reduces the amount of excess fuel, but also provides enhanced cooling through increased heat of vaporization. E10 to E15 blends have very little net effect on small engine reliability. So that's kind of the summary of things you might hear said about ethanol and what the facts are as opposed to the statements. I want to circle around now and go back to NASCAR a little bit. What our observations have been. We adopted ethanol fuel E15 in 2011. The conversion to the new fuel was seamless. We didn't make any design modifications to the engine. The engine power increased slightly. That's from the cooling effect of the ethanol. The spark timing, burn rates were not affected. Post-race piston hardness increased. That's because the E15 fuel provided more cooling than previous fuels without ethanol. Deposit buildup reduced. Deposit buildup is carbon that hasn't been oxidized, and as we saw in our little example here, ethanol does a great job of helping oxidize carbon deposits and reducing their buildup in the engines. Over 11 million miles now accrued in race conditions in NASCAR with zero mechanical issues attributed to E15. Tests with up to 30% ethanol have been performed without incident. Hopefully this is coming soon. So in conclusion, since we're in school, I have to give everybody a homework assignment. Ethanol is a great engine fuel. It is renewable, inexpensive, secure, and clean. All of you become advocates. Fight myths with facts. You lay it out. There are some disadvantages. There's a lot of advantages. I'm pretty sure that anybody who really sits back and looks at it from a scientific basis and weighs the advantages to the disadvantages will come to the same conclusion that ethanol is a great, great fuel. It's good for the consumer, it's good for our country. As we talked about a few times, listen to your wallet, and it will tell you that's the direction you want to go as well. Thank you for your attention, and I'd be happy to entertain any questions. Yes, sir.
So what's the overall goal of moving from up to 10% ethanol content to an E15?
Well, that's just the first step, hopefully, of many to come. But
I think that ethanol production is actually pretty inefficient as far as utilizing corn to make ethanol.
well, that's another myth that I probably should have talked about on here. the part of, you'll hear people make comments about, one, the price of corn being impacted, and two, you're using your food supply to create fuel. The corn that's used to make ethanol, first of all, is feed corn. It's cattle corn. It's not the sweet corn that you eat. And then what you do is you take the grain of corn and you extract just the starch out of it, which is usually about 6 to 15% of the corn kernel. You take the rest of the corn, you make what's called distiller's grains, which is a very protein-rich feed that's in demand internationally to feed cattle and other livestock, and it goes right back into the food supply then that generates the hamburgers and steaks and everything else that you might enjoy. So it's somewhat of a myth that the ethanol production is taking corn off of your table that you'd otherwise be eating, or increasing the cost of other products that rely on eating corn. As far as the increase from 10 to 15%, we have to work our way up slowly in ethanol percentage in gasoline, because the control systems of vehicles currently, and right now, E10, if you take an engine that was built, a car that was built back in the 70s or 80s, even in the early 90s, there's potential that you might have difficulty running that engine on E10, because the materials and the calibrations that were used when that engine that was built didn't comprehend that E10 was going to happen. Then around 2000, 2001, enough ethanol started getting in gasoline where the manufacturers figured out, we have to comprehend that. So the control systems were all built around E10, and in fact about 97% of the gasoline that's sold now has 10% ethanol in it. You have to look pretty hard around the Charlotte area to even find a fuel that doesn't have ethanol, and when you do, it's quite expensive. So right now everything's kind of optimized around E10. If you were to suddenly go and bump that up to E20 or E25, you'd have the same problem as we did when we went from E0 to E10, that the engines and the control systems are not designed to be able to accommodate that. There are some flex fuel vehicles out there that can handle wide ranges of from 0 ethanol all the way up to E85, but those are very few. So, that's sort of that's why we have to take this in small steps as opposed to larger steps, because larger steps will cause some issues with calibrations. Make sense? I want to say hi to Jared Bishop back there, by the way. He worked at ECR a couple of years for me, and good to see you, Jared. Okay, sorry. Anyone else? Yes, sir.
The higher cost of the pure gasoline or non-ethanol gasoline, is that not due to production, like supply and demand, or is that directly related to the higher cost of just using gasoline?
That's a good question. If you look on the commodities market, ethanol costs about $1, maybe Jamie would, $1.50 a gallon? About $1.50 a gallon. Gasoline without ethanol is running around $2, $2.10. Depending on what happens, that's pretty close, and that's the closest it's been for years. Certainly one of the questions you have to ask is, how secure do you feel with that gasoline price staying at $2 or $2.10 a gallon? It wasn't that many years ago, it was $4 a gallon. And unfortunately, we're not in control of that. If somebody in the Middle East decides they don't like you anymore and doesn't want to sell you oil, then that could go up very quickly. Whereas the price of ethanol isn't dependent on the international market, that's dependent on the domestic market. So that should be much more stable. So right now, the differential between ethanol and gasoline is probably about as low as it's been. Ethanol is still considerably cheaper. If you could get your gasoline for $1.50, I'm sure you'd be very happy. But just looking back over time and imagining what's going to happen go forward, I would expect that differential to increase once again.
I have a couple more questions.
Okay.
One is, it being water soluble, or water being soluble in that solution, what's to stop people from putting water into fuel mixtures?
Well, because it's only soluble up to a point. I was very careful in the video to say I was adding 0.9%, because if you add 1.5%, then you exceed the solubility and all the water falls out. So there's nothing to stop you from putting your 0.9% of it, but if you put too much in and it falls out, it's going to cause you a lot of trouble. That's...
I'm not going to put water in my gas tank. I'm just saying, what's to stop the retail?
Well, you say you're not going to, but in fact, what happens, especially if your car gets low on fuel, and then you're in a cool, damp night, and you're going to get some condensation, you're going to get some water in your fuel tank, and having a fuel in there that can handle that and absorb that is a good thing, in my opinion. So unbeknownst to you, you get water in your fuel, you just don't put it in there on purpose. Got another question too? 3 for the price of 1.
On a previous slide, you had said that the efficiency was about 35%.
Yes?
Was that in the racing motors, or was that in like typical consumer cars?
No, that's much better than what you get in a consumer. That's in a racing engine operating at wide open throttle. A consumer car is much worse than that, only because you spend so much time at part throttle. And when you're running at part throttle, you're having to suck air around the throttle, and there's a lot of work required to do that. So yeah, if you could average 35% efficiency in an over-the-road car, you'd be doing really, really well, or you'd be driving really, really fast. Yes, sir.
So how do you address the problems with regards to ethanol in like rubber components to older vehicles and farm equipment and small engines?
Yeah, well, that's one of the issues when we're talking about why don't we just go to E30 right now. If you do have vehicles that were made before 2000, there is that possibility. Alcohol can actually swell some of the rubbers, and that could potentially cause you some trouble. So when you start talking about older vehicles like that, you're best off trying to find some kind of ethanol-free gasoline. Anything that's manufactured since 2000, whether it be a small engine or an automotive engine, is designed and produced with the intent of not having any issues with alcohol exposure. So they're the types of the old Buna-N rubbers that absorb alcohols. You don't find them in engines anymore in this century.
So when we go to like say 30%, what's going to happen with all those vehicles and old equipment and stuff like that?
Well, the idea is not to go to 30% and not be able to get something less than 30%. The object is to offer you a choice. So if you've been in a sheet station, you'll see E10 and E15 and E85. The object is to have these service stations have some kind of a blending facility where they have a big ethanol tank and they have a big gasoline tank that has no ethanol in it. And depending on which button you push, that gets blended, and that's what's distributed out the nozzle. So the goal, hopefully, that would satisfy all consumer needs is not to replace low ethanol gasoline blends with higher ethanol gasoline blends, only to offer you a choice so that if you have a vehicle that can accommodate them, then you would be able to benefit from that economically. Okay? Yes, sir?
You say that ethanol is cheaper than gasoline. Can you comment on the effect of how we got here through subsidies and rebates and how much of a factor they are in that process?
Well, yeah, that's tough because there's subsidies for the oil industry as well. To try to get through all that is very difficult. Certainly, over the years, as the technology of producing ethanol from corn has gotten better and better, and plus the yield of corn crops themselves, the cost per gallon of manufacturing ethanol from corn has just continued to go down at a very rapid rate. Versus the cost of producing gasoline and refining has been fairly stable for many, many years now. As far as if you were to say, okay, let's take out from farm subsidies to tax subsidies to every subsidy possible, what then is the bottom line on costs? I'll have to admit, I don't know. I would be curious if anyone has. Have you seen studies that get into that?
Well, I used to be in the oil industry, so
Mm-hmm.
they have a point of view on this. But,
Yes.
the concerns about the ethanol was that if it was economic to do it, it would have happened by itself versus having to have subsidies to make it happen. And also, the price of corn did, in fact, go up quite dramatically because when farmland was being converted to corn because of this subsidy effect. And there was questions also about how much energy do you put into producing a gallon of ethanol, and is it really, I've seen studies that says you spend more diesel and gas to produce a gallon of ethanol than what you get out of it.
At one point, the price of corn did go up. I think it was more related, though, when you look back at what's happened to the price of corn since, was more related to the droughts and the conditions that we had for a couple of years there in the farmland, where the corn yields were significantly lower than they'd been in past years, where at the same time the demand for corn because of the ethanol industry was going up. But since then, with the higher density of farming and with the weather patterns returning to a more normal state, the price of corn is pretty darn low right now. Lower than it's been, historically low numbers as far as where we are. Ethanol industry versus big oil industry, that's a pretty brutal fight. I'd like to think that there's room for both in these blends, but obviously everybody wants everything. If you got 10% ethanol in gasoline, then the oil companies, that's 10% less product and less revenue that they're seeing, so they're going to fight that tooth and nail every way they can. So that's a battle that plays out.
The way you described it is having a gasoline retail station have a tank of ethanol and a tank of gasoline, and then the consumer gets to pick when the market decides.
Perfect. Perfect. Yeah, I would hope everybody would be in favor of that. Any other, yes, sir?
Yeah, I have two questions.
Okay.
One is, if I want to replace pure gasoline to E35, can you supply that amount of ethanol?
Can I supply it?
I mean, can we produce
Oh,
it?
can the world produce it?
Yeah.
If you were to say tomorrow that you're going to convert all E10 to E35, probably not. Right now we're in a situation though where we end up producing more ethanol than we can use. We have this blend wall, it's called, because E10 is legislated as the limit, and we're actually now producing more ethanol than we can use, so we end up exporting a lot of the ethanol we produce. But you're right, we do not produce enough to make 35% currently. So yes, that's something that if it happened overnight would be difficult to do, and we'd end up having to import ethanol, and that's going to impact the cost equation. So it would have to be something that would have to happen over time.
My second question is the flame speed of pure gasoline and the E15 or E10 inside the combustion chamber, the flame speed.
Yeah, and are you a combustion researcher? Well, you tell me what, because looking at engines where we.
And I think we talked about spark advancing.
Yes, and we have not changed even running E30 or running E85. I mean, it tends to, from everything that I've seen, I have not seen a difference there that I can quantify. What does the technical research show?
I'm asking, I have some experience of spark advancing with high comfort ratio.
Yes.
And then I got the same power. Because you lose power because of the calorific value, which is much lower than the gasoline. But taking advantage of the high efficiency and high proportion ratio, and giving with more time, you regain some of the power. How much that is the question that we can regain some of the power.
Yes, and typically as we increase compression ratio, we actually have to reduce spark timing because the more dense mixture burns faster.
So that's a calculation you have to do, that how much you advance.
Yes.
Initially I advanced 3 degrees too much, then I advanced 1.8, I found, yeah, that's fine. So
Where it came out for us, we were, at the time that E15 came out, we were making about 810 horsepower, and we went to E15, we made, just the fuel change alone, we made about 815. So that's basically 1/2 of 1% increase in power from adopting 15% ethanol. Small, but we get 1 horsepower, we do cartwheels down the hallway, so we'll take it.
thank you.
Yes. Anybody else? Even most of you stayed awake. Thank you all. Always a pleasure to come here.